Okay, good morning everyone. Let me share my screen. Okay, I hope I'm audible.
Yes, sir.
Yes, sir.
Okay, thank you. Okay, so today is the last lecture on DRAM. So this time I was initially it was planned like I'll not discuss much on DRAM, but that's why I discussed very less paper. Because last two time when I was teaching this course, I spent a lot of time on DRAM refresh, but this time I've spent very less time. So first, I think initial two recorded lecture I have uploaded on DRAM refresh. One is I think on write restoration, and another is on I think non-blocking refresh. And then I discussed some paper on row hammer attack, which is very important. And then after row hammer attack, today I am discussing one more paper, which is an interesting paper, easy but interesting paper. To improve the performance of DRAM, this has three major goal of this paper. So I'll discuss this paper. This paper also improve the performance. It also reduce the refresh overhead, and it can also handle the raw hammer attack. So, but obviously this paper has a lot of limitations. So limitations I'll discuss later. But if we ignore the limitations, then this paper is a very simple and interesting paper. And why I'm teaching this paper, there is one more motivation here. The motivation here is, if you when you'll understand this paper, you will realize that it's not required that you have to think very complex concept. If you can improve the performance with a simple design, then that is also acceptable. So that's why it's not required that every time you have to think a very complex design, that okay, the literature has been advanced so far, so the idea that I have to give, that my idea should be very very complex. It's not like this. Read the existing paper, try to find out their limitations, and always try to propose a simple idea. Why? Because by proposing a simple idea, if you can improve the performance, then it is always better. And if your idea is simple, then implementation will be also simple, and it will save your time. Okay. So this paper will, in short, we will say this paper is crow paper. And you can see the one of the author is Onur Mutlu. So this paper is from Onur Mutlu group. So ETH Zurich and Carnegie Mellon University, they both are this author Onur Mutlu was previously in CMU, and after that he moved to ETH Zurich. So both the authors from both the institutes are involved in this paper. I advise you to read this paper once, and when you will read this paper, most of the concept that is written here will be understandable to you, because the basic information which is required to understand these papers are already discussed in class. So now at this moment, when you will read a paper, you will also try to understand the flow of a paper, how a paper is written, how it is represented. So all these things important. So when you will read introduction, try to understand what are the different paragraphs in an introduction. Maybe first you read once and try to understand the concept. This is the main primary goal. But once you understand the concept, you read the paper again and try to understand how they have represented this paper. Each and every paragraph of introduction, I try to understand how they represented their work. So at the end of introduction section C, there should be the main goals. This paper makes the following key contributions. So this is a very compulsory section. So if you write a paper or you write a report, you have to make sure that this type of sections is there, or this type of paragraph is there at the end of your introduction section. So now one point they miss here, maybe here after here you can add one paragraph for organization of the paper, means which section, in section 4 what you explain, in section 5 what you explain, all these things. And before key contribution here, in this section, mainly in an introduction section, after reading this complete section introduction, people must know that what is the actual content of this paper. So try to understand this also, because when you will start doing research from next semester, these points are also very very important. Technical points are always important, but if you don't know this type of non-technical details, then it will be very difficult to do further research, because paper writing, image drawing, image plotting, all these things are also very important. Okay, so let us scroll down, because I'm not just explaining all this thing. I'll directly explain from this point. See, so far the way we have explained a DRAM is there are multiple. I'll concentrate only a single rank. So if there is a rank, then okay, maybe there is echo going on. Just let me mute one. Okay, yeah. So rank. If this is the rank, then there are multiple chips within the rank, right? And within the chip there are multiple banks. So all these things I have explained, but I said that we will not consider sub array. The a bank is normally divided into sub array. So the design that I have shown like this, that there are multiple rows here, multiple columns, and there is a row buffer here. I said this is a bank, but actually this is a bank is normally divided into multiple sub array. So you can see here they did the same thing here. Is a normal a bank is divided into multiple sub-array 0, sub-array 1, sub-array n minus 1. On there will be some global decoder, global row buffer, and also for each sub-array there will be a local row buffer also. So this is one sub-array. This is one sub-array. So the diagram that we know is this. So let us don't mix it. We'll consider this as a, if we consider this as a bank also, that is also fine. And if you consider this as a sub-array, then also it is fine. But just concentrate on this type of architecture where there are multiple rows and columns placed in a 2D manner, and for them there is a row buffer. And if you want to read something, then you have to activate a row. If you activate a row, then all the information will be available to the row buffer, right? And then from here you can read it. So all this information that I have explained in this class will use all those explanation here. Only difference here is we explained all these things as form of a bank, or you can say that we assume that one sub-array per bank. We assume that, but here they said n sub-array per bank. That is the difference. Okay, now let me, okay, yeah. Now, if this is your row buffer, and if this is your sub-array or bank, if we assume that one sub-array per bank, then you can consider this as a bank also. So I'm only concentrating on this diagram, not on the right side. So suppose I want to read something from row number 3, this row. So first I will send the I means a memory controller. So memory controller will send a activation command to this row, right? And when the activation command will be sent, so the word line of this row will be activated, right? Though I have explained this, but I am repeating here. The word line of this row will be activated. And once the word line of this row will be activated, the information will be available to the sense amplifier, right? And when the information will be available to the sense amplifier, the charge from this cell will be discharged for some moment, right? But after some time the charge will be again restored, because this line is keep on, right? The word line here is on. So since the word line is on, so first time when the line will be activated, the charges of this cell will be available in the sense amplifier, and after some time the charge will be again restored back. So this point you know, right? So and at the after this the data is also available in sense amplifier. The row is also available in sense amplifier, and also at the same time the row is again recharged. So that's why we normally say that when we access a particular row, at the same time it's also refreshed, right? That because data restoration happens. Okay, so and after this, if you want to read some other row, suppose after this all this operation, if you want to read row number 1, then first before all this we have to perform a pre-charge operation, right? Why pre-charge? Because pre-charge will make the sense amplifier put in half BDD mode, such that it can sense another row. So all these things, if you go this type of diagram, first they say activate command, controller will send. If you want to read a row, first controller will send activate command, and after activating activate command, what will happen? This line, let me again explain it. So activate commands means this line will be activated, This what line will be activated, and then these charges of this cell will be flow through this bit line to this sense amplifier, right? This time is called TRCD time. I hope you know this, right? The moment the memory controller will start activating a row, and from that moment the charges become available to sense amplifier. This part is called TRCD time. So if you go here, it is written as TRCD time. After TRCD time, the data will be available in the sense amplifier. Okay, but not the restoration phase. Data is only available in sense amplifier after TRCD time. But at this moment, the cell in the original row here in this row are now discharged. So it will take some time after this to restore. So restoration phase, you can see here after TRCD time, you can see this time is required for restoration. This time is required for restoration. So when the data will be restored, at the same time you can start reading the data. If someone wants to read a particular column, then first it will activate. Now after TRCD time, data is available in the sense amplifier. So the data restoration and data read can be performed simultaneously. So data restoration will be performed at the same time. We can send a column address here, and if we want to read a particular column, then we can read that. Okay, so you have to understand TRCD is the important time. After TRCD, if you want to read, then you can perform read operation, and after the read operation, here you have to perform a pre-charge operation. Why this pre-charge operation? Pre-charge operation is required to perform to activate one more row, right? Before this, the row, the sense amplifier must be in half BDD mode. So that is called pre-charge. So the time required from here, that one TRCD, then a read command, and after read and the complete, this is called one read cycle, or this time is called TRES. This complete time is called TRES. So I think all these timing parameters I've already explained in a separate lecture, but I'm explaining the important timing parameters here because this, based on this timing parameter, the paper is proposed. So from all this timing parameter, the two timing parameter that is very important for this paper is TRCD and restoration. So you can see that we are assuming that restoration will be complete before within the TRES time. So this is quite possible that the restoration will be completed within TRES time. Okay. So from this diagram, you just remember what is called TRCD time and what is called restoration time. Restoration time is not included in TRCD. After TRCD time, only the data will be available in the row buffer, and then it will take some more time to restore the data back into the row. Okay. So let me just zoom it out again. So far I have not explained anything about this paper. These are the basic concept, and you can also see they have explained all this basic concept in a background section. Background section means all the information that those are required to understand this paper, they have included in background section. When you will write a paper, you will also understand that if all the information that is required in your paper, you can explain all the basic information in a section called background. So read this section once. I'm not explaining it in more detail because I think all the necessary things I've explained. So let me go directly to the main concept of this paper: copy row DRAM. That's why they call it scroll, copy row DRAM. So how they have designed it: suppose this is your sub bank, this is your sub array. Okay, so what they will do, they propose here that the rows in the sub array, they will divide into two parts. First part is called regular row, and second part is called copy row. So copy row will have very less number of rows. So normally number of rows in a bank are more than 500, maybe 512. Suppose if there are 512 rows are there, out of 512 rows, only I think 4 to 8 rows will be copy rows, not all rows. So you have to understand that this copy row part is very, very small as compared to the regular row part. But what they did in their main proposal in this paper is divide the rows in a survey into two groups. One is called regular rows and another is called copy rows. And for regular rows, there will be two decoder. One decoder that is local row decoder that is already there. That decoder will be used only for regular rows. And there will be a separate decoder that is called crow decoder will be used for copy rows. So there are two parts: regular rows and copy rows. I hope this part is clear. And for there are two separate decoders also there for regular rows as well as copy rows. Okay. Now The main, as you said, there is a term called copy, right? Copy means if there is a row here, you can copy the content of this row in a copy row. Suppose I want to copy the content of this row. No, it will be better to say first row. I want to copy the content of first row to the first copy row. Then how to perform this copy? So they said a very interesting this concept. They said first the memory controller will activate this row. When the memory controller will activate this row, the data will be available to the sense amplifier after TRCD time, right? Data will be available in sense amplifier. Which data it is? This data is the data of row 1 of regular row. I'll say R1. Regular R1 is available here. And I want to copy the content of R1 in C1 also. So what we'll do, after sending a activate command for R1, okay, after some time, means the memory controller will send another activate command for this row. Activate command for this row. So before receiving this activate command, assume that the sense amplifier is already filled with the content of R1. At this time, if this row will be also activated, then what will happen? During the restoration phase, both row will be restored from the information that is stored in sense amplifier. This is a very interesting point. I'm saying that first time what they will do, they will activate R1. The moment they'll activate R1, it will take TRCD time to let that information available in sense amplifier. And after this, what they will do, they will not deactivate R1. R1 will be still activated because there are two separate decoder. Through the second decoder, after TRCD time, they will activate the second row also. When the both rows are activated, okay, so both rows are connected. Activated means that transistors are now on, right? The switch of each transistor now on. At this moment, after TRCD time, the restoration phase will start, right? So during the restoration phase, when the both lines are activated, so the rows, the both row will be charged with the information that is stored in sense amplifier. So in this way, the content of R1 will be copied into the in the row C1. So this copy information is very important. Why? You will understand now. So the main contribution of this paper is there are three contributions. First contribution is called Crow Cache, I think. Crow Cache. So in Crow Cache, what they did, this copy row they use as a cache memory, not cache memory, yeah, but some kind of cache. So why there? What is the purpose of this? So every time if you whenever there will be if a row is activated, then the copy of this row will be also placed here. Okay, so if they activate this row, then at this time, this row, a copy of this row will be created here also. So now there are two copy exists for this row. Okay, so at this moment, what will happen? If next time if you want to activate if you want to read something from this row, then both row will be activated simultaneously. And if both row will be activated simultaneously, then TRCD time will be reduced. Why? Because TRCD time is required once you activate a bit line, or sorry, word line, then all the charges will go through the sense amplifier, and sense amplifier will sense this charge and amplify it to either binary 0 or binary 1, right? So the charges, when it will flow through the bit line, this time, that is called TRCD time, will be reduced if the same information, this copy row means these the row numbers R1 and suppose and row number C1 now storing the same information. And if we want to read something from R1, what we will do, we will activate both R1 and its copy row C1 simultaneously. And if we activate both the row, then the same charges, means charges that is stored here and charges that is stored here are same. So same charges will be available through this bit line. So what it will do, it will reduce the TRCD time. So that is the main concept of Crow Cache. So if you want to access a row and the content of that row is available in the copy row, then you can activate both the rows simultaneously such that you can reduce the TRCD time. That's it. That is the main concept of Crow Cache. So how to maintain it? To maintain this, what they are saying that there in memory controller there will be a table called crow table. I'll not explain it in more detail, but in memory controller there will be a table called crow table, and you can see for in this table there will be for each the entries are there for the entire for each DRAM channel. So you can see for each this type of table will be there in memory in crow table in memory controller MC. And it is n-way associative. N-way associative means if there are n rows here, n copy rows per subbank, then there will be n ways here. So basically there will be one row for each sub-array here, one row for each sub-array, bank id, sub-array id, so one row for each sub-array. So if there is a, suppose this is a memory controller, and memory controller request for r1, that I want to suppose not r1, there is a address ad1, right? Ad1. So memory controller receives a request for address 1. So memory controller has to send this address to main memory to read the content of this address. So suppose this address is mapping in R1 of this subarray. So what the memory controller will do, first it will go to a particular subarray. Suppose the subarray number is the first subarray. So it will search in all the, that if the row this R1 is available here or not. If the row R1 is available here, then it will understand that a copy row of this is also exist. So what memory controller will do, instead of activating only R1, it will send activation command for both R1 and C1 simultaneously. And what it will do, that it will send activation command of both R1 and C1 simultaneously, and because of that it will reduce the TRCD time. So this is the main logic. So to implement this, first thing is copy, right? When to copy. So they say that the copy is every time whenever they will there is a new request is there, the new row is activated, then they will make a copy of it. But you can see here that the number of copy rows are very limited. I said, right, the regular row is the main rows of this DRAM, so number of regular rows will be very high as compared to the copy rows. So there are very limited number of copy rows are there. As I said, it should be from 4 to 8. So if there are very less number of copy rows, then obviously there will be conflict. And if there are conflict, then we need to maintain a replacement policy. So they also maintain a replacement policy that if suppose the copy rows are full here, and at that time suppose these two content are copied here now. So now let me change the color. Now this row is activate, there is a request to activate this row from regular row. So if we want to activate this row, you cannot make a copy of this row in copy row because copy row is full. So at this moment what we have to do, we have to replace the content of this copy, the one of this row. Maybe suppose they will use if they use LRU, then maybe they will remove this one, and in place of this they'll copy the content of this row. So here, if you want to replace something, no write back is required because it's a copy content. Original content is already there, right? If you want to remove the first, this is C1, right? If you want to remove C1, then you no need to restore it back to R1, right? Because C1 is just a copy of R1. Even if you remove C1, then the R1 is still there. So there is no data corruption. So if you, so what they did the same thing. If your copy row is full, and if you want to copy another regular row in copy row, then you have to just use a replacement policy, choose a victim, and then override the content of this victim with the new content. So this is the main concept of Crow cache. So application of Crow. First, they have explained the generic term of Crow. So Crow has three properties. First is called Crow cache, then Crow ref, and then Crow. I think I forgot. I'll tell you here. So application of Crow. So first, it's called in-DRAM caching. I hope you are understanding in-DRAM caching. So as I said, there are two parts, right? Regular row and copy row. So copy row is just storing the information. If it is R1, then same copy is available in C1, right? So that's why they are saying this is in-DRAM caching. They are using a cache within the DRAM. But there is a small difference between the term cache here. When we'll say about cache in computer architecture, we say that first search in cache, right? If there is a miss in cache, go to other memory, right? But here a cache, it's not like that we have to first search in the cache. It's not like this. Here cache means there is a copy exist here. So if there is a hit in the cache, then we will simultaneously activate the cache content as well as the actual DRAM content. It's not like that if there is a hit in the cache, then we will always read it from the cache. If we do this, then there is no benefit because both are of same thing. So every time you have to understand the in-DRAM caching concept. They said in-DRAM caching means if there is a hit, then it will only reduce the TRCD time. And if it is no hit, then original TRCD time will be required, because if there is no hit, then only one row from the actual DRAM. This is the DRAM, or you can say regular rows, right? So if there is no hit in the in-DRAM cache, then only regular row will activate. Okay, no reduction in TRCD time. And if there is a hit in the in-DRAM cache, then the both regular row as well as the corresponding copy row will be activated simultaneously. So it will reduce the TRCD time. That's it. Okay, so first see here for in section 4.1, they have explained the first concept that is called crow cache. So that I have explained here crow cache, but only there are some limitations here. So one major limitation here will be copying the cache. I said when you want to copy the content of R1 into C1, first a memory controller will activate R1, then after some time the data will be available in row buffer, right? And to copy it, then after TRCD time, the memory controller will also activate C1. So now since both R1 and C1 are activated, so during the restoration phase, the data will be restored back in both the rows C1 and R1. But to do this, the restoration phase slightly increase. The restoration time, that is to restore the data back into one row, that time is and to restore the data back into two rows now is little higher. Okay, so if you read this section, I think they have explained it how much higher it is. They're saying it is 18% higher. So it means that they are increasing the restoration time by 18%. So that is a disadvantage, right? So they are saying that once a copy of the row exists, so next time when you will activate the row, then you can activate both rows simultaneously. It will reduce TRCD time. That is fine. But first time when you are copying the row, then it is increasing the restoration time by 18%. So how to handle this? They said that even after increasing it by 18%, it is giving benefit, because it is happening that most of the time once you make a copy of a row, that row will be accessed more than one time in future. So in all the future activation of that row, if the copy is available in the copy row, then it will reduce the TRCD time. This is one point option. And then another option they have said here, that you can also reduce the restoration latency. How? I think this point is related with the recorded lecture that I've uploaded last week. I think when I said I explained a paper where the paper was based on write restoration time. So here also they are saying that when we'll restore the charge back into the rows R1 and C1, it is not required to restore it completely, right? If this is your capacitor, and it is not required to restore it completely. They are saying that okay, restore it up to this much, which is enough to retain till next refresh period. So how refresh happen? If periodic refresh is happening at this, then after TW time a refresh will happen here. After TW refresh will periodic refresh will happen here, right? So suppose restoration is happening here. So at this point, it is not required to restore it completely. What is the logic of restoring it completely? Because very soon there is a periodic refresh happening here. So just restore it enough such that it can hold the charge till the next refresh period. So they are saying they will partially restore it. So if we'll partially restore it, then the 18% overhead that they are saying here, this 18% overhead, they can reduce this overhead, because they will not spend all the much time on restoring the complete cell. They will only restore it partially, such that it can reach till the next periodic refresh point. So those concepts they have explained here in this section. I think reducing the restoration latency. Okay. And you can see section 4.1.4. The next section is evicting entry from crow table. Evicting entry from crow table. Obviously, they should go for a replacement policy, right? If the crow table is full, it means the copy rows are full, then you have to go with a replacement policy. So that part I have explained. So I think with this, I think the concept of crow cache is clear. The main idea of crow cache, I'll repeat it again, because this is the main heart of this paper. That you can see here there are two rows in a survey are divided into two parts: regular rows and copy rows. Regular rows are the main rows. Copy rows are actually very less number of rows are considered as copy rows. There are two separate decoder used. One is the regular row decoder, which is the original decoder, and a separate small decoder is they have designed for copy rows. Okay. So now the main concept here is when we access a row, then that row the first time when we access a row first time, a copy of that row is created in copy row. Okay. So and next time when we activate this row, then the memory controller will find from this crow table that okay, a copy of this row exists in the copy table. So the both row will activate simultaneously, and if both row activate simultaneously, then it reduce the TRCD time. That is the benefit. And how to do this? To do this, when to copy a row, how to copy a row, right? What are the limitations and what are the challenges to copy a one row from regular to copy row? And if the copy rows, since the number of copy rows are less, when the copy rows will be full, how to handle this? So all these challenges I've explained. But the main concept here is reducing the TRCT time by simultaneously activated two rows, the original row and the copy row. Okay, so this is the concept of crow cache. So now the next concept they use, next point they use is the same structure. It can be also used to handle the weak rows. So I think this concept, I don't know I have explained it or not. If we design a DRAM, then some of the and we say the retention time means, as I said here, that here if we refresh all the rows, then after some time here we will refresh again. So it's called TRE, refresh window, right? Then again here I'll refresh all like this. So normally I if you see, we say this is 64 millisecond, right? After a 64, every 64 millisecond you have to refresh a row. If you don't refresh it within 64 millisecond, then the content of this cell of that row may lose the charge or lose the data, right? But actually this is the worst case scenario. Suppose out of all these rows here, these two rows are weak rows. These two rows are weak rows. So the 64 millisecond is for this two weak row. If you don't refresh this weak row within 64 millisecond, the content of this two row will be discharged. But other rows are strong rows. So it has been found that the strong rows can hold a charge till 3x time. So suppose so this, if it is strong row, then maybe if I ignore this two weak row, then you can increase the restoration time to this 3 cross 64 millisecond, 3 cross 64 millisecond. So if you can do this, assume that these two weak rows are not there. So if you do this, then what is the advantage? Advantage is you are reducing the number of refresh, right? So the last week also I've uploaded a lecture on how to perform non-blocking refresh, because when we perform a refresh, the entire DRAM device is blocked, right? For normal read write operation, it is performing the refresh. You cannot perform normal read write operation. This is the first disadvantage of refresh. Second disadvantage here is when you perform read write operation, it consumes some energy, right? Because this is called dynamic energy consumption. So if you can reduce the number of refreshes, then first point, that is the blocking time will be reduced, and also the energy consumption will be reduced. So the main point here, the 64 millisecond is taken. It's the worst case time, and that time is normally the considered as the restoration time of a weak row. So that the weak rows are very, so if we design a survey, in every survey almost I think 4 to 8 weak rows are there. So this paper says, when you read this paper, they say the number of weak rows are very less. It is less than 4. They assume this. But if you read, I'm not giving any citation here, but yes, it is. There are some other papers where people say that no, the number of weak rows per survey can go up to 8. Okay, and as the technology size is shrinking, so what is happening is technology size shrinking means more and more surveys we are placing in the same chip area. So it means that the space between two rows is also decreasing. So as for that, it is highly likely that in near future the number of weak rows may also increase more than 8 parts array. So for this point, from this point, there is it is also a big area of research, that how to handle these weak rows. So last year, one of my students, that is Sudarshan, who was a batchmate of Prathamesh. So Sudarshan worked on this weak row management. This time Shamiksha Burma is working on weak row management. So this handling weak rows is an important area of research here. So what I'm saying, again back to this point, that let us remove the cross, because you cannot say that weak rows are not there. It was just a assumption. Suppose these two row are weak. So how to handle these two row? Because these two row need refresh within 64 millisecond, but other rows are strong rows and they need refresh in 3 cross 64 millisecond. So what this crow is saying that, okay, so with this idea knowledge, let us go to this diagram. So in this diagram they said, okay, Fine. If these two rows are weak rows, then let us disable this two weak row and copy them here. Okay, these two weak rows will be disabled. These two will be disabled. ये काम नहीं करेगा. Will be disabled, and they will copy in the copy rows. And then then this will work same as regular R. So suppose this row is R1 and suppose this is R2. Suppose so memory controller has the crow table, right? So if there is a request for R1 or R2, then memory controller will send the request to throw this copy row decoder. And if the request is for some other rows, then again the normal decoder will handle. So this technique they are saying is crow ref. So crow ref is designed to handle the weak rows, but you have to understand that you cannot combine crow cache and crow ref. Crow cache is not handling weak rows, right? Crow cache is only reducing the TRCD time. And here crow ref is not reducing the TRCD time, because in crow ref there is no copy row concept. There is no copy row concept. Here we are actually moving. There is a difference between copy paste and cut paste, right? So you can say in crow ref R1 and R2 we are cut pasting it to the copy rows. Actually we are not making a copy. It is not Control C, it is Control X, right? Okay, so that is called crow ref. So since the number of weak rows are very less in the sub-array, so the copy rows will be, they claim that copy rows will be enough to hold all the weak rows, but still there are some limitations. First limitation is if these copy rows, some of these copy rows are weak rows, then how to handle it. So those points they missed here, and they said that they are saying that no, since the number of normally they say that they take copy rows at 8 copy rows they assume, and they say the number of weak rows will be 2 to 4 they assume in this paper. So even some of the copy rows are weak, then also we can handle it. That is their problem statement. But obviously you can understand there are limitations, because if there are 8 copy rows already there, and some of your 8 weak rows are there, here there are 8 weak rows, and all of your copy rows are not strong, then may be a problem, because they choosing copy rows at in a particular section, right? The last rows are called copy rows here. The rows which are near to sense amplifier, they are considering these as copy rows. So if some of them are weak, then how to handle it? So obviously there are limitations, but let us not discuss the limitation first. Let us try to understand the paper. The paper is very good and very interesting paper. Every paper has a limitation. If we propose a paper, if we propose a design, our design also have some limitations. So don't think about the limitation first understand the paper. So crow ho gaya, crow cache and crow ref both have explained. So after this, if you read the end of this chapter, they propose a common combining this, they propose crow cache plus ref. This is written in the last section. So what is crow cache plus ref? So I hope you are understanding what is called crow cache, right? Crow cache means they will copy the content in the copy row such that they can reduce the TRCD time next time. This is called crow cache. And crow ref you also understand, right? Crow ref means if there are some weak rows, then they will move. They will not copy. They will move those weak rows to the copy rows. And as I said, normally copy cache and crow cache and crow ref are two different design. You cannot combine them. But at the end of this paper, they said no, we can combine it. How? Because the number of copy rows, though in this diagram they are showing only 2, but in experiment they use 8 rows here. So if there are 8 rows here in copy rows, and they said that no, number of weak rows will be hardly 1 or 2. So suppose if the number of weak rows are 2, then only 2 rows will be copied here, and still there are 6 rows remaining in the copy rows, right? First they said there are 8 rows in copy rows, and out of 8 rows you can see that the entire regular rows in here, only 2 rows are weak. So they will copy these 2 weak rows in copy rows, but after copying this also there are 6 rows remaining. So in these 6 rows can be used as crow cache also. So in these ways they say that since the number of weak rows is very less, even after moving those copy rows in the even after moving those weak rows in the copy rows, then also there will be some copy rows remain, and those copy rows can be used as crow cache. So that's why crow ref and crow cache can be combined. And they said this combined crow plus ref is giving better improvement. Okay, because it is handling both weak rows as well as crow cache. But obviously, again, here you can understand the limitation is if the number of weak rows increase. If the number of weak rows are also 8, then if you want to go with crow cache plus crow ref, then the number of copy rows required is 8 plus 8, right? Because there are 8 weak rows, so you have to copy all the 8 weak rows here in copy rows, first point. Then you need to efficiently handle crow cache, you need maybe you need 8 more cache. So 8 plus 8, or at least 8 plus 8 plus x may be less than 8, but it is some extra rows are required. So the disadvantage here is if you use these rows are not extra rows, right? When a DRAM will design, suppose these are the total rows. Out of total rows, you have selected that okay, this much row I'll use as copy rows. So if you select 8 rows as copy rows and total number of rows are n, then actual size of this is now n minus 6, right? Suppose n minus 8, right? If your total copy rows are 8, then it is n minus 8. Now if you say that now while combining these two technique, I want 16 copy rows, then your total number of rows will be n minus 16. These are the original rows, right? So if you reduce the original rows, then also it may you are reducing the capacity of the DRAM, right? First it was n minus 8, and now you are saying 8 plus 8, so you are reducing the capacity of the DRAM. So if you keep on decreasing the capacity like this, then the advantage that you are getting from copy a crow cache or crow ref or crow cache plus ref, those advantages will be negligible, or those advantages will be overruled by the capacity that you are decreasing from the DRAM. So that is also a limitation. So as I said, in this paper, let us go with their assumption that number of weak rows are very less. If we go with this assumption that number of weak rows are very less, then crow cache plus ref is a good technique. Then if there are 8 rows here, use 2 rows for copy, use next 6 rows for cache. That is fine. So I think I have explained 3 design here: crow cache, crow ref, and crow cache plus ref. They have one more design here. I forgot that what they say this. So let me scroll down and I'll see this. I don't know what they say this. Crow ref. I have explained you crow ref. After crow ref, oh okay, they have not given any name for the third one. They said mitigating row hammer. So how this same technique can be used to mitigate row hammer? Again, I'll scroll back to the diagram here. It is always easy to explain the concept from diagram. So if suppose a row hammer, suppose this particular row is aggressively activating this row. I'm saying about this row. This row is aggressively activating. So if this row is aggressively activating, then these 2 rows are victim rows, right? So they are saying that once it is detected a row is aggressively activating, then what we can do, then we can copy the content of these 2 victim rows in copy rows. These 2 victim rows will be copied here. Victim rows will be copied here, and you can say these victim rows are now disabled. So even if the bit are flipped here, then it's not a problem because we are not using them. It is not like the original crow. After move here also we are moving the regular rows. It is not copying. Once a row hammer is detected, the content of this victim row will be copied to the copy rows. Okay, and now these are the victim rows are here now. So even if we aggressively activate this row, even someone aggressively activating this row, the neighboring rows are not here, so it cannot create any major problem. But again, the limitation here is if the attacker attacks multiple aggressive row, multiple row within a same refresh window. If you read the twice paper, I think in twice paper or the paper that I've explained, my paper RHLM in last lecture, it has been found that at max 20 rows are possible to attack. 20 aggressor row possible in a particular window. So agar 20 aggressor row ja raha hai, 20 aggressor row means if even we consider that 2 neighbor rows, then also there are 40 neighboring rows, 40 victim rows. So there is no place for 40 victim rows in copy rows, right? So obviously this will this is a major disadvantage. But when you read the paper, you understand that they have also not given much attention on row hammer. They have just written that it may be possible, but they also written that it needs some more exploration. So based on their assumption, since they have also not given much attention on row hammer part, they just say that maybe we can use it for detecting row hammer or mitigating row hammer. But the main concept here is crow cache, crow ref, and crow cache plus ref. So if I scroll down the paper here, I think last section is for crow cache plus ref. Um, yeah. I'll advise you to read this. See, 8.3 combining crow cache and crow ref. So this paper is very interesting. It's published in, I think, in ISCA. So, but when you read this paper, I said the paper is very easy to understand. That's why I'm advising you to read this paper once. And if you have any problem you face here, then you can discuss with me. So I'll after if you understand the concept of crow, then I'll quickly explain you the work that is done by Sudarshan uh, of my student. So Sudarshan was an MTech student here in the same batch of Prathamesh. He was the batchmate of Prathamesh. Currently, Sudarshan is working in Intel. He recently joined in Intel. So that's why if you do a good work in computer architecture, and it's not just you are open for higher educations, you are also open for architecture companies. Okay, so and also maybe you know that your immediate senior Bharat is also now means got a job in Intel. Okay, so in this paper we propose on top of Crow. This paper is based on the limitation of Crow. So for exam purpose, this In-DRAM, we call this paper as In-DRAM. So I'll not include this paper as a part of your coursework. And also since this paper is not published yet, this paper is under minor revision. Just we received a minor revision in last week. So it will take 1 or 2 weeks more to publish the paper. So I'll at this moment I am not sharing this paper with you. If anyone interested, then let me know. I'll share, because this I'll not consider this paper as a part of your coursework. Sorry, part of this syllabus of this course. So what we are doing here in WinDRAM, maybe I'll scroll down. I'll go to an image. Maybe this. Let me go to a image. Yeah. Suppose this is also similar to Crow. As I said, it is work is inspired from Crow only. So what we said here in Crow, this type of designs are there, right? There are some copy rows are there, but these copy rows are always close to the sense amplifier, right? So as a result, the main problem of Crow is they cannot handle both, because if we assume that number of weak rows are also 8, right? Number of weak rows are also 8 or more, and as the technology is decreasing, it may be possible, as I said, in future the number of weak rows will also increase even more. So in that case, crow cache plus ref is not practical, because if we go with crow cache plus crow ref, then it will increase, then it will reduce the size of the regular rows. And if you reduce the number of regular rows, then your DRAM capacity is decreasing. So as I said, that disadvantage will overrule the advantage they are getting from these techniques. So here what we said in WinDRAM, that suppose there are some weak rows available here. Don't go with this copy row decoder. Assume that this decoder is not here. This is not here. So suppose these are the 4 weak rows here. So what we said that we'll use these 4 weak rows to create the copy rows. So our copy row will be not here. So in Crow, what they use, that copy row will be at the end and very near to the sense amplifier. No, in our case, it will not be here. What we'll do, that we'll create a In-DRAM cache. I hope you are now understanding what is called In-DRAM cache. The copy rows are called In-DRAM cache, right? In Crow cache. So now we'll design In-DRAM cache with these weak rows. Okay, with these weak rows we'll design In-DRAM cache, and then other rows are now regular rows. So what will happen here? So it will work both as crow ref and crow cache. How it will work as crow ref? So crow ref, what they do that in crow ref, they separate the weak rows, and then the regular rows are separate, right? And they can increase the retention time of regular rows. Same here, we can see that we are separating the copy rows. So regular rows we can refresh in 3 into 64 millisecond, regular rows, okay. And weak rows we are using as a copy rows here. So what we will do as copy row, in copy row, if there is a normal row, suppose, let me change the color here. So suppose this is a regular row, right? So when there will be activation in this regular row, what we will do, we'll copy the content of this row in the copy in the in-DRAM cache, right? In a weak row now. So next time when we want to activate this row, this blue row, then we'll activate similarly as there is a crow table, right? Similar way we are also maintaining a table like crow table. So like crow table, so when we next time we want to activate this row, this blue row, okay, so at that time this row as well as the corresponding copy row will be activated simultaneously. So also it is reducing the TRCD time. Only difference here is that we are using all the weak rows as copy rows. So since we are using all the weak rows as copy rows, first we are easily handling the weak rows. We no need to refresh all the rows in 64 millisecond. We will refresh it in 64 3 into 64 millisecond, that is fine. And weak rows here are copy rows. And also one more advantage here, since weak rows reduce the charges very fast, but since we are using them as cache memory, it means that they will be regularly accessed, right? And we already know that if we access a row, then that row will be automatically refreshed. Since all the rows in copy rows, suppose let us go back to crow cache again. So if we go back to the crow cache, so these are the copy rows, right, in crow cache. So these rows will be regularly accessed because what we will do, which type of rows will be there in here? Copy of the regularly accessed rows will be there in copy rows. So it means that these rows will be regularly accessed. If these rows are regularly accessed, they will be refreshed automatically. So what we are doing, we are not refreshing these weak rows. We are not refreshing. We are assume that these will be automatically refreshed when they are accessing it. In some case, in some particular situation, if these rows are not refreshing, then we'll let them discharge. Why you will let them discharge? Because this is just a copy, or one more copy is already there in suppose what I said, there was R1 and this is C1, right? So if we let the C1 discharge, no problem, we have a copy exist in R1. Just we need to inform the memory controller that okay, C1 is now discharged, so you have to understand that copy is not exist. That is the only limitation here. So that we use some counter, and we based on this counter we have implemented it that okay, if a weak row is discharging, then we will allow it to discharge. We will not perform any periodic refresh. So this is the main concept of WinDRAM. And one more advantage of WinDRAM is in crow there is a disadvantage here, that if you want to access a row, what they said that if this content of this R1 is also available in C1, then first they have to send the address of R1 to activate this, and at the same time after some time they have to send one more row address for the copy, because there is single bus here, right? Only one bus here connecting memory controller and DRAM device. So how to send two row address with one bus? So that is the limitation of crow. So either you have to increase some lines here, you don't need to double the bus length, you need to add some bits here in bus length. This is one way. So another way is you have to add some delay, and you have to use you have to add some delay. If original time is t, then you have to use t plus delta to send two address one after another. So the best design they said is they will increase some additional 2-3 lines extra in this bus to send two addresses, like original row address and the copy row address simultaneously. But even it is increasing the overhead. This is the first point. Second point is they are maintaining the table in the memory controller. So the way we know how our modern desktops are, suppose this is your motherboard, and your motherboard has 4 slots of RAM. So each slot is for one DIMM, right? And this is your processor. So processor is fixed, right? But here, as maybe you have installed 2 RAM in these 2 slots, but here there is no RAM installed. That is also fine, right? Our motherboard, if in your desktop computer these two RAM slot are there is no RAM inserted, then also it will work because there are 2 RAMs here. But if you want to maintain crow table in processor, because normally memory controller is part of processor, right? So you have to, in OS case, there are how many DIMMs are here? There are 4 DIMMs. So there should be storage for crow table for all the 4 DIMMs in memory controller, right? Because you have to go, because who knows, after maybe today you will go to market and purchase one more RAM and you will install it here. If you are doing it here, then your memory controller must have support for CRO table of this newly inserted DIMM. So every time memory controller has to go with host case storage. So that is the disadvantage of CRO. One more disadvantage. So what we did in In-DRAM, we have not used a memory controller to store this type of table. If you read the content of twice paper that I've explained in last class, that twice they used, if this is a rank, inside this rank there is a module here called RCD, right? So we stored our table in this RCD module inside a DIMM. So it is this table is local to each DIMM. So we are not giving the overhead to memory controller. So there are two advantages here in DRAM over CRO. First is this, we are not giving much overhead to memory controller, so the area overhead of memory controller will reduce. This is the first point. Second point here is, if the weak rows are less, then our policy and CRO are almost same. CRO cache per step. I'm saying obviously our policy is better than CRO cache. If we say about CRO cache or CRO ref, sorry, it is CRO ref, In-DRAM is better than any of this. But if you combine these two, CRO cache plus ref, then this is the last technique of CRO paper, right? So combining this, then with combined version, In-DRAM and this combined version has almost similar advantage if the weak rows are less. But as I said, our paper is based on the assumption that, as I said, assumption is different. CRO assume that weak rows are less. Our paper, we assume that weak rows are 8, or in future it may increase also. In such case, our work is much better than this combined work, because this combined work is wasting too much rows from a DRAM as copy rows, right? So it is reducing the capacity, and WinDRAM is not doing this. So how much it is wasting? That just I'll give and I'll stop here. Suppose there are 8 weak rows. So 8 weak row you have to move from. Suppose there are 8, but not 8. I'm saying 2. Why 2? Just to explain it. So these 2 are weak rows. So I'll stop this and I'll copy it here. Okay. So how many rows we are wasted? Suppose initially the rows were 8, already now it is n minus 4. Why n minus 4? 2 you used as copy and 2 you blocked as you make cross. So already you have wasted 1 n minus 4. Now again, and now you have only implemented CRO ref. Now if you want to implement CRO cache, then you need 2 more copy rows. So total will be n into n minus 6. So a lot of rows you are wasting. So if the number of weak rows are 8, then maybe n minus 24 rows will be there. So 24 rows you are wasting if you combine CRO cache and CRO ref in future. And here in weak rows, in WinDRAM, in our technique, if you go, then only 8, it will be only 8. So total number of rows available will be n minus 8, which is much larger than the CRO. And that's why WinDRAM is giving better advantage. Obviously, WinDRAM has also a major disadvantage, and it is the designing the decoder. If we go for the CRO, it is very easy to design a copy decoder because the rows are at the end and very near in a contiguous location, right? So decoder designing hardware overhead is less, but in our case, the weak rows are distributed throughout the sub-array. So in that case, a decoder design is complex, and we accept that the hardware overhead of designing a decoder will be more. But with this limitation only we propose, and we specifically mention in our paper that this is the limitation. So if someone can design an efficient decoder for the copy rows in WinDRAM, then it will give better performance. So that's it. I'm stopping it here. So if you have any question, you can ask now also, or you can ask me after reading these papers once also. So again, I'm repeating, this WinDRAM paper is not in your syllabus, but if you want to read further in this area, if you want to work further in this area, then you can read this paper also. So I'll not share WinDRAM paper. If you want to read it, then let me know. I'll share with you personally. So I'm stopping it here. If you have any question, you can ask.